Okay, so you send us a stack of research papers and articles, even
Yeah.
your own notes, all about this really cool intersection of deep learning and symbolic reasoning. Basically, how to get the best of both worlds in AI. So buckle up because we're about to take a deep dive into what matters most from all this material. And trust me, it gets really interesting.
Absolutely. What we have here is like a quest for the holy grail of AI, combining the robust pattern recognition of deep learning with the logical structured reasoning of symbolic AI. It's a challenge, but the potential is enormous.
So deep learning is great at spotting patterns, right? Like it can tell a cat from a dog in a picture, but it doesn't really understand what a cat or dog is in the same way we do.
Exactly. And that's where symbolic AI comes in. It excels at representing knowledge as symbols and rules. Think of it as the language of logic and relationships.
So how do these two very different approaches work together? The sources you shared actually outline a fascinating map of the field, breaking it down by architecture.
Yeah, and one of the things that really jumps out from these sources is just how much work is going into addressing the limitations of purely neural models.
Okay, so let's talk about those limitations. What are some of the big ones that the research highlights?
Well, one of the most fundamental limitations is this issue of structured reasoning. Neural nets are really good at pattern recognition, but they struggle with tasks that require hierarchical thinking.
Like understanding the relationships between different concepts.
Exactly. Or understanding how things are organized in a hierarchy.
So it's like they can see the individual pieces of a puzzle, but they have trouble putting those pieces together into a coherent picture.
That's a great analogy. And this can lead to all sorts of problems. For example, neural nets often mix up correlation with causation.
Right, just because two things happen together doesn't mean that one causes the other.
And yet neural nets often fall into that trap, which can lead to some pretty misleading conclusions.
Okay, so structured reasoning, that's one big limitation. What else?
Another big one that comes up again and again is the issue of data need. Neural nets are incredibly data hungry. They often need massive data sets to learn effectively.
Which is not always feasible in the real world.
Exactly. Not every problem comes with a giant, neatly labeled data set just waiting to be devoured.
And even when those data sets are available, collecting and labeling all that data can be incredibly time-consuming and expensive.
It's a real bottleneck for a lot of AI applications.
Okay, data need check. What else are we missing?
Well, then there's the challenge of knowledge integration. It's surprisingly difficult to directly insert human knowledge into a neural net.
Like expert knowledge or even just common sense?
Exactly.
Yeah.
We humans have all this knowledge that we've accumulated over lifetimes of experience, but it's really hard to translate that knowledge into a format that a neural net can understand and learn from.
It seems like a missed opportunity. If we could find a way to teach them what we already know, wouldn't that make them so much more efficient and capable?
Absolutely. And that's one of the big motivators behind Neuro Symbolic AI. Now, another limitation that often comes up is the issue of explainability. Neural nets are often seen as black boxes, meaning we know they work, but we don't always understand how they arrive at their conclusions.
Right. It's like they give us the answer, but they don't show their work. And that can be a bit unsettling, especially when we're talking about AI making decisions that impact people's lives.
It's a critical concern that's driving a lot of research into making AI more transparent and accountable. And finally, the sources point out the lack of guarantees with purely neural models.
Okay. In what sense?
Well, since they're based on probabilities, there's always a chance, however small, that they might make a mistake even after extensive training.
So there's no way to be 100% certain that they'll always do the right thing.
That's right. And that can be a bit unnerving, especially in areas like self-driving cars or medical diagnosis, where even a tiny error could have serious consequences.
Makes sense. So we've got a pretty clear picture now of why purely neural models, while impressive, aren't the whole story. How does symbolic AI fit into this puzzle?
Symbolic AI takes a very different approach. Instead of learning from patterns in data, it uses logic and symbols to represent knowledge and reason about the world.
So it's like the difference between learning by experience and learning by studying a rule book.
That's a great analogy. And because it's grounded in logic, symbolic AI has some inherent advantages. For one, it can generalize from limited data.
No more data-hungry AIs. I'm liking this already.
And it's also highly interpretable, meaning you can actually trace the logical steps behind its decisions.
No more mysterious pronouncements from the AI overlords. We can actually understand their reasoning. That's a big step forward in terms of trust and transparency.
Absolutely. Symbolic AI also makes it much easier to incorporate expert knowledge directly into the system.
So we can actually teach them what we know rather than just hoping they'll figure it out on their own. But I'm sensing a but coming. There's always a catch, isn't there?
Well, the main challenge with symbolic AI is scalability. As problems become more complex and involve a huge number of variables, symbolic AI systems can get bogged down, becoming computationally very expensive.
So it's great for tasks that require precise logical thinking, but maybe not so much for those massive data-driven problems.
That's a fair assessment.
Yeah.
And that's where this exciting field of neurosymbolic AI comes in. It's all about trying to combine the strengths of both approaches, the scalability and pattern recognition of neural networks with the reasoning power and transparency of symbolic AI. It's like building a hybrid engine for intelligence.
I love that analogy. So we're talking about merging the intuitive data-driven side of AI with the analytical rule-based side. But how does that actually work in practice?
Well, the sources you share lay out two main architectural categories for neurosymbolic AI: composite frameworks and monolithic frameworks. And those are where things start to get really interesting.
Okay, let's unpack those, starting with composite frameworks. What are those all about?
In a composite framework, the neural and symbolic parts are kept separate, like two specialists working on different aspects of the same problem. They might exchange information and influence each other, but they each have their own distinct roles to play.
So it's a bit like a collaboration rather than a full-on merger.
Exactly. And within composite frameworks, there are two main approaches: direct supervision and indirect supervision. Direct supervision is like having a teacher guide the neural network, providing extra feedback during training to make sure it aligns with the rules and logic defined by the symbolic system.
So the symbolic part acts like a quality control system, ensuring that the neural network's output makes sense from a logical perspective.
Precisely. And the sources you shared actually highlight a few really cool examples of direct supervision in action.
Okay, I'm ready to hear about them. Let's dive into the world of direct supervision.
Welcome back. Last time we were talking about this exciting frontier of neurosymbolic AI and how it's trying to bridge the gap between the pattern recognition power of neural networks and the logical reasoning of symbolic AI.
Right, we were just getting into those composite frameworks where the neural and symbolic parts work together but remain distinct, like two specialists collaborating on a project.
Exactly. And remember, within composite frameworks, there are two main strategies: direct supervision and indirect supervision.
You were about to give me some real-world examples of direct supervision. You know how I love a good example. Makes it all click into place.
One framework that's been getting a lot of buzz is called the teacher-student framework. It's a pretty intuitive concept. The symbolic system acts as the teacher, training the neural net to mimic its behavior.
So it's like the symbolic system is showing the neural net the right way to think based on its own logical rules and knowledge.
Exactly. The symbolic system generates predictions, and those predictions are used as the ground truth to train the neural net. It's a bit like an apprentice learning from a master craftsman. This approach has been particularly successful in areas like natural language processing, where you might want a neural net to learn how to identify different parts of speech or extract meaning from text.
That makes sense. So the neural net is learning by example, trying to match the output of the symbolic system.
Precisely. And because the symbolic system is grounded in logic and rules, it can steer the neural net towards more consistent and reliable decisions.
Teacher-student framework check. What other intriguing direct supervision approaches are out there?
Well, here's one that I find particularly fascinating. It's called deep probabilistic logic, or DPL for short. What's really cool about DPL is that it goes beyond just training the neural net. It actually uses the neural net's output to refine the symbolic system as well.
Wait, so it's a two-way street. The neural net is learning from the symbolic system, and the symbolic system is learning from the neural net. That's wild.
Exactly. It's like a continuous feedback loop where both systems are constantly improving each other.
It's like they're having a conversation, challenging each other to become better thinkers.
I love that way of putting it.
Yeah?
And this approach has been shown to be really effective in tasks like entity linking, where you need to figure out which mentions of a named entity in a text refer to the same real-world entity.
Okay, DPL is definitely blowing my mind a little bit. Are there any other direct supervision frameworks that we should talk about?
Yes, there's one more that I think you'll find interesting. It's called Concordia, and it takes a very flexible approach to combining neural and symbolic systems.
Okay, I'm all about flexibility. Tell me more about Concordia.
Concordia actually allows for 3 different ways to connect the neural and symbolic parts. First, it can use the neural net's output as input for the symbolic system, providing it with additional information to reason about.
So it's like the neural net is giving the symbolic system a heads up about what it's seeing in the data.
Exactly.
Right.
Second, much like the teacher-student framework, Concordia can use the symbolic system to guide the neural net's training, providing feedback and nudging it towards more logically sound decisions.
Okay, so those first two connection methods sound familiar. What's the third way that Concordia is unique?
Well, the third way is where it gets really clever.
Mm-hmm.
Concordia uses a special gating network to dynamically decide how much weight to give to the predictions of the neural net versus the symbolic system.
Wait, so it's like it's choosing the best expert for the job depending on the specific situation.
Precisely. And this gating network isn't just fixed. It's trained along with the neural and symbolic systems, so it actually learns how to make those decisions in a way that optimizes the overall performance of the system.
That's so cool. It's like having a manager who knows which team member to call on for each task.
Exactly. And because of this flexibility, Concordia has been used successfully in a wide range of tasks, from computer vision to recommendation systems.
Okay, so we've got teacher-student, deep probabilistic logic, and Concordia all doing some pretty impressive things in the realm of direct supervision. They all sound pretty amazing, but are there any drawbacks to this approach in general?
Of course.
Right.
One of the main challenges is making sure that the symbolic system can provide feedback that the neural network can actually understand and learn from.
Right, it's like they speak different languages, one based on logic and symbols, the other on patterns and numbers.
Exactly. Bridging that communication gap can be tricky.
So we need a good translator, someone who can speak both languages fluently.
Precisely. Another challenge is that the symbolic system itself can become quite complex and computationally expensive, especially as the problems we're trying to solve get more intricate.
So we might run into that scalability issue again.
It's definitely something to keep in mind. But despite these challenges, direct supervision is a really promising area of research in neurosymbolic AI. It's already produced some remarkable results, and I think we'll see even more exciting breakthroughs in the years to come.
Okay, so we've explored the world of direct supervision. Now let's shift gears and talk about indirect supervision. How is this approach different?
In indirect supervision, we take a more divide and conquer strategy. The neural network is primarily responsible for pattern recognition, extracting features and insights from the data, while the symbolic system handles the higher-level reasoning and decision-making.
So it's like the neural net gathers the evidence and the symbolic system plays the role of the judge, deciding what it all means and what actions to take.
That's a great way to visualize it. For example, imagine a self-driving car. The neural net might be responsible for identifying objects in the environment, like cars, pedestrians, and traffic lights. And then the symbolic system would use that information along with its knowledge of traffic laws and safety protocols to decide how to steer the car.
Okay, that makes perfect sense. But if the symbolic system is making the final calls, how does the neural net get trained in this setup?
That's where things get really interesting. In indirect supervision, the training process is guided by the concept of abductive reasoning.
Abductive reasoning. That sounds very Sherlock Holmes-esque. What exactly does it involve?
You're on the right track. Abductive reasoning is a way of working backward from an observation or conclusion to figure out the most likely explanation. It's like solving a puzzle, where you have the final picture, but you need to figure out how all the pieces fit together.
So it's not just about the neural net making accurate predictions in isolation. It's about making predictions that lead to the right actions according to the symbolic system's logic.
Exactly. And that's how the neural network gets trained. It's rewarded for making observations that support those desired outcomes, even if those observations aren't perfectly accurate on their own.
It's all about being helpful in the context of the overall task, even if you don't have all the pieces of the puzzle perfectly figured out. I like that. Can you give me a concrete example of how this might work in practice?
Sure, let's go back to that chess game analogy. Imagine you have a neural net that's learning to analyze chess positions. Instead of just training it to label images with checkmate or stalemate, you would show it a board position and ask the symbolic system, using abductive reasoning, what sequence of moves would have led to this position.
So the symbolic system is basically working backward, using its knowledge of the rules of chess to figure out the most plausible explanation for the current state of the game.
Precisely.
Yeah.
And then that information, that sequence of moves, is used to train the neural net, guiding it to recognize patterns that are consistent with the rules of chess.
That's brilliant. So even though the neural net might not understand chess on a conscious level, it's being subtly guided to make observations that are useful for making decisions within the framework of the game.
You got it. And this indirect supervision approach can be applied to all sorts of problems, from medical diagnoses to financial forecasting. Anywhere you have a complex system with rules and logic that can be used to guide the learning process.
Okay, I'm sold on indirect supervision. It's a really clever way to blend the strengths of neural and symbolic AI. Now, what are some of the most exciting frameworks out there that use this approach?
Well, one of the pioneers in this area is a system called Deep Problem. It's a really elegant framework that combines deep learning with probabilistic logic programming.
Okay, I need a quick refresher on probabilistic logic programming. It sounds pretty intense.
It might sound intimidating, but the basic idea is quite intuitive. Probabilistic logic programming is a way of dealing with situations where we don't have complete information, where there's uncertainty involved.
Yeah. So it's like saying, we're not 100% sure about all the facts, but based on what we know, here's the most likely scenario.
Exactly.
Mm.
And that makes it a perfect fit for combining with neural networks, which are also inherently probabilistic in nature.
Makes sense. So how does Deep Problem put this all together?
In Deep Problem, the neural network is used to provide probabilistic facts to a logic program. These facts might represent things like, I'm 80% sure this object is a car, or I'm 60% sure this person is smiling.
So the neural net is giving its best guesses based on the patterns it sees in the data?
Exactly. And then the logic program takes those probabilistic facts and uses them to reason about the situation and make decisions, just like a detective piecing together clues.
Okay, I'm starting to see how this works. The neural net provides the raw data, the logic program provides the reasoning, and together they arrive at a conclusion.
Precisely. And Deep Problem has been used successfully for a lot of different applications, from understanding images to controlling robots.
Deep Problem check. What other indirect supervision frameworks are making waves?
Another one that's worth mentioning is called abductive learning, or ABL for short. ABL uses a really interesting technique called pseudo-labeling to train neural networks.
Pseudo-labeling. Now that's a new term for me.
Well, the basic idea is to generate fake labels for data that doesn't already have labels. It's like creating extra training examples out of thin air.
Sounds like magic. But how do you make sure those fake labels are actually useful?
That's where the symbolic system comes in. In ABL, the pseudo-labels are generated using, you guessed it, abductive reasoning.
So the symbolic system is using its knowledge and logic to say, based on what I know, these unlabeled examples should probably have these labels.
Exactly. And then the neural network is trained using those pseudo-labeled examples along with any real labeled data that's available. It's like giving the neural net some extra practice guided by the wisdom of the symbolic system.
I love that analogy. It's like having a tutor who can help you fill in the gaps in your knowledge. But I'm guessing there are some potential pitfalls with this approach.
You're right. One of the challenges is that the pseudo-labels can sometimes be wrong. If the symbolic system's knowledge is incomplete or inaccurate, it can lead to the neural network learning the wrong things.
So garbage in, garbage out, as they say.
Exactly.
Yeah.
So it's crucial to be very careful when using pseudo-labeling. You need to make sure that the symbolic system has a solid understanding of the domain and that the pseudo-labels are generated in a way that's consistent with the overall goal of the task.
Okay, that makes sense. So we've got Deep Problem and ABL both doing some pretty cool things with indirect supervision. Are there any other frameworks in this category that are worth highlighting?
Yes, there's one more that I want to mention. It's called Neurolog, and it builds on the ideas of Deep Problem, but takes them to a whole new level of flexibility and scalability.
Okay, I'm always up for more flexibility and scalability. Tell me more about Neurolog.
What sets Neurolog apart is that it's not limited to probabilistic logic programming. It can actually work with a wide range of symbolic reasoning systems, which makes it incredibly versatile.
So it's like a universal adapter for neurosymbolic AI.
That's a great way to put it. And Neurolog has been used for all sorts of tasks, from image captioning to robot planning.
Okay, Neurolog is definitely on my list of things to explore further. So we've covered 3 really interesting indirect supervision frameworks: Deep Problem, ABL, and Neurolog. It seems like this whole area of research is really pushing the boundaries of what's possible with AI.
It is. Indirect supervision is a really exciting approach because it leverages the unique strengths of both neural and symbolic AI, allowing them to work together seamlessly. And I think we're just scratching the surface of what's possible with this approach.
It feels like we're on the verge of some truly groundbreaking discoveries in this field.
I completely agree. The potential is enormous.
Yeah.
And speaking of pushing boundaries, are you ready to delve into the world of monolithic frameworks where logic is literally baked into the very structure of the neural network?
I'm ready to have my mind blown. Bring on the monolithic frameworks. All right, so we're back and ready to dive into the deep end of the pool. Those monolithic frameworks where neural and symbolic AI aren't just collaborating, they're like literally fused together.
This is where things get really futuristic. We're talking about building AI systems where Logical reasoning isn't just an add-on. It's woven into the very fabric of the neural network.
It's like we're trying to create a digital brain that can think both intuitively and logically at the same time.
That's a great analogy. And as you can imagine, it's an incredibly complex challenge. But the sources you shared highlight some truly mind-bending approaches that are pushing the boundaries of what's possible.
Okay, I'm ready to have my mind bent. Hit me with the most mind-blowing approach.
Well, one of the most fascinating concepts is the idea of logically wired neural networks. Imagine a neural network where each individual neuron represents a specific concept or logical atom.
So instead of just being these abstract mathematical units, the neurons actually have meaning in the context of our logic.
Exactly. And the connections between these neurons represent logical relationships. For example, you might have a neuron that represents the concept of cat, and that neuron would be connected to other neurons that represent related concepts like mammal furry or pet.
Okay, I'm starting to see how this works. So the structure of the network itself embodies the logical relationships between different ideas.
Precisely.
Ah.
And by activating or inhibiting these neurons in specific patterns, the network can perform logical operations, like deducing that if something is a cat, it must also be a mammal.
It's like the network is thinking logically just by the way it's physically structured.
That's the idea.
Yeah.
But training these logically wired neural networks is where things get tricky. Traditional neural network training methods like backpropagation don't always play nicely with these more structured networks.
So we need new tools and techniques to teach these networks how to reason logically.
Exactly. And researchers are drawing inspiration from all sorts of fields like logic programming and constraint satisfaction to come up with innovative ways to train these networks. It's a really exciting area of active research.
Okay, logically wired neural networks are definitely blowing my mind. What other approaches are researchers exploring in this quest to create monolithic AI systems?
Another really promising avenue involves something called tensorized logic programs.
Tensorized logic programs? That sounds vaguely familiar, but I need a little refresher on what tensors are all about.
Well, in essence, a tensor is a multidimensional array of numbers. Think of it like a matrix, but with potentially more than just rows and columns.
Okay, so it's like a super-powered spreadsheet.
You could say that. And the beauty of tensors is that they can capture the complex relationships between different elements in a logical program.
So how do we actually convert logic into this numerical tensor format?
There are a bunch of different techniques, but one common approach is to represent logical atoms as vectors and then use tensor operations to capture the logical relationships between them.
So we're essentially encoding the logic into the mathematical structure of these tensors.
Exactly. And once the logic program is represented as a tensor, it can be processed by a neural network, just like any other kind of data.
It's mind-boggling to think that a neural network could be doing logical reasoning through the manipulation of these numerical tensors.
It is. And this approach has opened up a whole new frontier, allowing us to combine the raw processing power of deep learning with the elegance and precision of logic.
Okay, monolithic frameworks are living up to the hype. They're definitely pushing the limits of what we thought was possible with AI, but I'm guessing they also come with their fair share of challenges.
You're absolutely right. One of the biggest hurdles is scalability. These monolithic frameworks, because they're trying to do so much within a single integrated system, can be computationally very demanding.
So even though we're gaining all this power and flexibility, we might be sacrificing some efficiency.
It's a classic trade-off.
Yeah.
And researchers are working tirelessly to find ways to make these frameworks more efficient, but it's an ongoing challenge. Another challenge is that this whole field is still relatively young. We're just beginning to uncover the true potential of monolithic frameworks, and there's a lot of work to be done in terms of developing new techniques and building a solid theoretical foundation.
So it's a bit of a wild west out there, but with a lot of potential for groundbreaking discoveries.
Exactly. It's a frontier full of possibilities.
Okay, enough with the abstract. Let's talk specifics. What are some of the most exciting monolithic frameworks that are out there making waves in the real world?
One that's been getting a lot of attention is called neural theorem proving, or NTP for short. It's a really clever system that uses deep learning to enhance traditional logic-based theorem provers.
So it's like giving those logic-based systems a turbocharged neural engine.
That's a great way to think about it. In NTP, the basic building blocks of a logic program, predicates and constants, are embedded into a vector space, and a neural network is used to compute the similarity between them.
So instead of just looking for exact matches, we can now consider the meaning of those symbols, even if they're not perfectly identical.
Exactly. It's like giving the system a deeper understanding of the relationships between different concepts. And this has proven to be really helpful in dealing with noisy or inconsistent data, which is something we encounter all the time in real-world situations.
The real world is messy and full of ambiguity, so that's a valuable feature. Okay, NTP is clearly a powerful tool for automated reasoning. What other monolithic frameworks are out there pushing the boundaries?
Another one that's worth mentioning is called Logic Tensor Networks, or LTNs for short. LTNs combine the power of fuzzy logic with deep learning to create a system that can handle uncertainty and reason about complex relationships.
Fuzzy logic. Remind me what that's all about.
Fuzzy logic is a way of dealing with concepts that aren't black and white. It allows for degrees of truth. So instead of just saying something is true or false, we can say it's somewhat true or mostly false.
That sounds a lot like how we humans actually think about the world. Things aren't always so clear-cut.
Exactly. And that's what makes fuzzy logic such a powerful tool for AI. In LTNs, each logical atom is represented as a vector, and each predicate is represented as a function that operates on those vectors.
Okay, so we're back to representing logic through vectors and functions.
Right. And then fuzzy logic operators are used to combine these representations, allowing the network to reason about the truth of logical statements, even when there's uncertainty involved.
So it's like building a fuzzy logic engine directly into the neural network.
You got it. And this approach has been really effective for tasks like knowledge-based completion, where you're trying to fill in the missing pieces of information in a large database of facts.
LTNs definitely sound like they have a lot of potential. Any other monolithic frameworks that we should have on our radar?
Yes, there's one more that I want to highlight. It's called TensorLog, and it takes a very practical approach to this whole idea of combining logic and neural networks.
Practicality is always a good thing, especially in the world of AI where things can get pretty abstract.
Yeah, absolutely. What TensorLog focuses on is using neural networks to efficiently implement the inference mechanisms of logic programming.
So instead of trying to reinvent the wheel, they're just making the wheel spin faster using the power of deep learning.
That's a great way to put it. And this approach has proven to be very scalable and efficient, allowing TensorLog to handle much larger knowledge bases than some other monolithic frameworks.
Okay, TensorLog sounds like a real workhorse in the world of neurosymbolic AI. What are some of the real-world applications it's been used for?
It's been used for all sorts of tasks, from question answering to natural language understanding. It's a really versatile system that showcases how logic and deep learning can work together to solve complex problems.
Wow, this has been an incredible journey through the world of neurosymbolic AI. We've covered so much ground, from the fundamental limitations of traditional AI to the cutting-edge research that's pushing the boundaries of what's possible. It's a field that's absolutely exploding with new ideas and possibilities.
It really is. And what I find most exciting is that this isn't just about making AI smarter. It's about making it more trustworthy, reliable, and even understandable to us humans, which is going to be key for AI to truly reach its full potential.
Well said. So for our listeners, if you're as fascinated by this field as we are, I encourage you to dive deeper. Explore those research papers, check out the code for some of these frameworks, and who knows, maybe you'll be the one to make the next big breakthrough. Thanks for joining us on this deep dive into the incredible world of neurosymbolic AI.
It's been a pleasure.